So today we're going to talk about how to write untestable code, because we're all so good at it. How do you write hard-to-test code?
Code that's very monolithic.
It's monolithic, OK?
Non-deterministic.
Non-deterministic, exactly. OK, that's good. So here's something interesting, right? When asked these questions on an interview, most people have a really hard time answering me how exactly they would go about writing hard-to-test code, even though the code they write is really hard to test. So we are intrinsically good at this, even though we don't know how exactly we're good at this thing. It's kind of like a spider weaving a web. You know, it just knows how to weave a web, and you can ask him, how did you do it? And the spider says, I don't know, it just kind of works. So this is what people normally say, like make things private, use the final keyword, have long methods, and you pointed out doing stuff monolithically. That kind of goes with long methods, etc. Non-determinism, that's a good one too, that I don't have. But here's the thing, that the real issues of unit testing, and that is mixing the new operator with your business logic. And we're going to get to why exactly that's a problem in a second. Looking for things, and we do this in our code all the time, you know. Doing work in a constructor, that makes it so that it's really hard to instantiate things inside of your test. Having a global state, which is essentially where all of the uncertainty comes from. Singletons, which is just another name for global state. And static methods, which is essentially procedural programming. And one thing that you can think about is, suppose somebody gives you a purely procedural code. How would you test it? And it turns out that I have no idea how to test purely procedural code. Because in order to test something, I need to isolate something. In order to isolate something, I need to have some kind of a seam. And seam in the object-oriented world is my polymorphism coming to play. Something that I don't have in procedural code. Yes?
Why exactly static methods hard to test? I guess
because you don't have a seam. So here's the kind of the problem. I don't want to get into it too much because there's a couple of slides later that we're going to cover this. But the basic issue is this. If you have a leaf method, such as math.absolute value, piece of cake to test, right? Because it's a leaf. It doesn't call anybody else. But if you have a method that is way up in the call hierarchy, and you're trying to invoke that method, and you want to prevent that method from calling, I don't know, a database or something like that, there is no way for me to prevent that call from happening because all the methods are static, and there's nothing for me to overwrite. So yes, in the simplest case, when you have a simple leaf method like an absolute value or such a thing, piece of cake. But when it comes to be a more complicated program, the answer is no. So the worst thing is trying to test a main method. If you're trying to test your application from the main method, good luck. Chances are you cannot do it. So we don't really know how to do it. The other thing is deep inheritance hierarchies, because it's essentially the same problem. I cannot divorce myself from the inheritance at runtime, right? At runtime, I would like to instantiate a small portion of my application. And if the class I want to test is X, and X inherits from A, B, C, D, E, F, G, then whether I like it or not, I'm testing all the other classes as well. And so deep inheritance hierarchies is something that makes it really hard. So notice these two lists. Most people actually cannot answer the question of what makes code hard to test, even though we do this all the time. So we kind of want to talk about this a little further. Oh yeah, and last one I forgot, our good old favorite, too many conditionals, which is the if statement. But anyways, let's get down this into further on. Oh wow, this is a really long list. So here's the thing. What can I tell you about writing tests? Turns out nothing. Like, I cannot teach you anything. There's no magic to writing tests. Absolutely none. There's a couple of it's a couple of tools like easy mocking framework and stuff like that. But for the most part, there is no secret knowledge I have about testing. None whatsoever. What I do know a lot about is how to write testable code. And that kind of is the core of the problem, which is most people assume that I'll write code, and I'll throw it over the wall, and here comes my test engineer, and he'll write some tests. Except at that point, it's too late, because the code is already written in such a way that the test engineer cannot write a good test. It's too late. And it makes it kind of worse, because the place where the mistake is made, which is writing the code, and the person who feels the pain of hard-to-test code are not the same people. And as a result, it's really hard to kind of affect change in an organization like that. And so we're all kind of guilty of this.
Is it on?
Yes.
Okay. But for unit tests, it should be ideally the same people, right? So the people who do it. Yeah.
Exactly.
So you're talking about other tests as well, or?
No, this is kind of an introduction. Absolutely, we want to get everybody to unit testing level. And in the unit testing, it has to be the same person. I'm just trying to point out how the other kinds of tests don't really work. So we're going to talk about it in the unit test in a second. So just hold on 1 second. So glad to know that you're ahead of the curve, though. It's good. So what can I tell you about writing testable code? Well, it turns out we can talk about what good OO is and how it helps testing, and we're going to devolve into this thing a little bit. And we can also talk about something we call dependency injection. Sometimes I feel like with dependency injection, I'm selling a snake oil because it fixes so many things. But it does actually work. Of course, there's the test-driven development, which, as you point out, we want to take the unit testing folks together. You want to make sure that the person who writes the test and the person who writes the code is really the same person, and you want to go definitely into the unit testing route, which we'll get to in a second. So here's the thing. There is absolutely no secret to writing tests, none whatsoever. The only secrets there are as to writing testable code, and that's kind of what we want to talk about. And it sounds like you're already ahead of the game and you already know that the answer is unit testing, but for most people, they aren't actually that far along, and most people are still stuck on the premise that there's just some secret sauce to testing, which there isn't. So how do we, I like to think about unit testing. Imagine you want to test a car, and somebody says to you, please test the car for me to make sure the car works. Everybody who's new to testing will immediately say, ooh, I know, I'm going to build a framework. In the context of a car, I'm going to build something where the car can sit on top of, and I'm going to build some machine that will pretend to be a driver and will turn the steering wheel and push the brake and the gas and play with the knobs, and that's how I'm going to test that the car works. And this is what basically scenario test is. And a test like that is actually pretty cool because it does actually prove that the car works. The problem with it is the execution, and that is these tests are horribly slow because let's say you want to prove that the car all-wheel drive system works correctly. Well, now you have to get the car into where there is ice. So now what are you going to do? Drive it into a refrigerator? And then you want to make sure that the car can start, it doesn't overheat at really hot temperatures in the desert. Now what are you going to do? Drive it in the oven? Right? Even if you can do that, even if you can build all these frameworks, these things are going to be really, really slow, and they're going to be flaky. There's so many things that can possibly go wrong. You're testing the whole system end to end. Like maybe the oven's broken. Maybe it's not the fault of the car. So the problem with scenario or large-scale tests is that they're flaky. They're slow and they're flaky. And it's not uncommon for you to have to take several hours to execute all of your scenario-based tests. Not very useful. So then you say, well, maybe we can do something better. So we kind of mentioned this, that you discover basically that your tests are slow and you discover the tests are flaky, right? We kind of covered this. So this is the kind of the first stage of unit testing. The people discover, hey, tests, good. So we can automate this thing. Here's the good thing. You have a really high confidence when things work that the thing actually worked, that the car actually worked, right? Whereas if something goes wrong, you're not really sure if the problem was the car or is it because the designer has moved the knob 1 inch to the left and all of a sudden the framework can't grab anything. You're just really not sure of what exactly went wrong. And a lot of times, things are just flaky. And you don't really know why because there's so many variables come into play. So it's really hard to reproduce failures. So suppose if it's flaky and it fails and you're like, okay, let's do it again. And all of a sudden it works this time. And you really have no idea how and why and so on. So I'm just pointing out how troublesome that is. So then you kind of think about it and you say, well, maybe instead of testing the whole car, I can break the car down into parts and test them individually. So maybe instead of pretending to be a driver where I turn on and off the radio, maybe I can take the radio out in isolation and hook it up to maybe an oscilloscope for the output of the radio and remove the knobs, and instead of the knobs put some kind of a analog to digital converter that directly controls the knobs. And now I can test the radio in isolation, independent of the car, and I can bake it, cook it, and do all kinds of things with it to make sure that the radio works just as we planned. And we can do the same exact thing for the engine, for the transmission, and for any other component in the car that's a large-scale component. And so what you discover is things get a lot better. Again, when the things are green, you're pretty sure that the thing works. When it's red, you're also pretty sure that something went wrong, because you took so many variables out and you only have these large-scale systems that you're pretty sure that something's broken. The problem with that is, suppose the radio doesn't come on, like, good luck figuring out which part of the radio is broken. The engine doesn't start, good luck figuring out what exactly is wrong with the engine. Like, it's much better than having the whole car and pretending to be testing that, but it's not quite what we want, right? So we call this medium-level test or functional test, because you take a single functionality and try to test it in isolations. From a software point of view, this is kind of like taking your app, and instead of replacing the outside servers, like the authentication server, you're going to replace with an in-memory fake LDAP or something like that, which auto-authenticates, and so on. So you basically focus down on individual pieces and you test them in isolation. So then you say to yourself, wait a minute, if going from large-scale testing to medium-scale testing, we got better at this, maybe we can go in further and go down to individual components. And in the world of software, that's individual classes. So instead of testing that the engine works as a whole, maybe I can basically have individual tests that verify that the piston is of the correct shape, that the oil is present, that the spark plug has the correct clearance, and so on and so forth. And I'm just individually testing all these pieces. And I know that if all of those pieces are correct, then I am very, very confident that the engine will actually start. And if I discover a case where the engine doesn't start, I can always go back and figure out what was the root cause and add a test for that root cause. So it turns out that these kinds of tests are great because they're super fast. Right? This is our unit test. From a software point of view, this is where you're testing individual classes. They're really good because you have really high confidence. The tests are really fast. We went down from several hours to run and verify that the product works down to seconds, literally seconds. And now you can do crazy stuff. You can say to yourself, maybe I can hook up my save button, so every time I save the code, it just runs all the tests, because they're a couple of seconds, what's the problem? So imagine writing code where you just code along and say, oh yeah, okay, I think I'm ready to save. Control S and voila. And you know immediately if you broke something or not. It's a nice world to be in, right? And then really the other nice thing about it is, if the test fails, it directly points to the cause, right? If the spark plug clearance is not good, you know exactly what needs to be replaced. Like, there's no question about this, right? So if a function that is supposed to be doing sorting fails and it doesn't sort properly, like, you know exactly where to go look for the error. Like, in most of the cases, you don't even need a debugger to figure this out. So this is the promised land of unit testing. So, as I said, most people, when you first tell them, write me an automated framework for testing, they'll immediately think, ooh, I got to pretend to be a user, and I got to write some kind of a framework. And we call that a scenario-based testing. And there's so many problems with that I think your effort is better spent on unit testing. If you have unit testing and you have nothing else, you're way better off than if you have just scenario testing. Now, of course, you're better off if you have unit testing and functional testing and a little bit of scenario testing. But for the most part, you want to have unit testing. Now, when they build a car in the factory, here's something fun that happens. They put the car together. They have individual tests that prove the pieces work. And they have one final test. And the final test is they take a key, they shove it in the ignition, they turn, and they drive it to the parking lot. If that works, that means a lot of things. That means that the battery got hooked up and it's charged, right? It means that the steering wheel is hooked up, that there's gas in the engine, and so on and so forth. There's a whole long list of things that kind of means that it kind of works. Now notice, we didn't prove that all these things work under all conditions. All we're proving to ourselves is that they got hooked up properly together. And that's the purpose of a scenario test. You just want to kind of make sure that things got hooked up properly together, and you have separate unit tests to prove that all the pieces work. And you kind of have functional tests to kind of prove that individual related pieces work, like the radio works in isolation, the engines work in isolation, the transmission works in isolation. So therefore, I just want to make sure it's hooked up together, and I'm pretty confident the whole system's going to work as well. So all of these different levels, as I said, are important because you have all different probabilities that you're going to find a bug. But they're different kinds. As I said, unit testing is all about, does it do the right thing? Whereas in the other extreme is it hooked up properly? And then everything in the middle is kind of, the medium test, they kind of test a little bit of both. But again, we just want to have these kind of extremes. We don't want to test everything at once because it becomes hard to test. Turns out that if you, there's a way to code so that you separate out the hooking up problem from the functional problem. And that way of coding is actually called dependency injection. We'll look at it in a second why that is important. We kind of already touched on this, but I'm just going to cover this again, and that is you really want to have a large number of unit tests. Typically, the number of unit tests is going to be semi-equivalent to, or the number of lines of code of test, unit test code, is going to be approximately equivalent to the number of lines of code in production code. Pretty much, give or take, in the same ballpark. Which also pretty much translates to about the roughly same number of test cases to function methods you have. But that does not imply that you actually want to have one test case per function. You just have approximately the same number of test cases. You want to have a lot smaller set of functional tests that kind of test that the individual subcomponents kind of work together properly. There you're starting to get more in the business of, is it hooked up properly? When I pass this object to this object, does the other object expect to get it in the correct state? That's kind of what you're testing over there. And then the scenario test purely is test in the form of, does the pieces kind of talk to each other how we expect it? Can a server come up in isolation kind of a thing? We really don't go into the details of replicating things. I'm going to skip over this, and I'm going to come down to here. So, unit testing. We decided in here that unit testing is a good idea. So, you have a test driver, the JUnit, and you have class under test. And you apply some stimulus to the class under test. You call some methods, right, on it. And then you assert that something expected happened. Piece of cake? Easy? So, why are we having this discussion? Why is this so hard? What's the problem with this model right here? Yes? Things often have dependencies. Exactly. So the reality of it is that the class under test usually has these other classes it depends on. And guess what? Those things depend on other classes. So I do something benign, like I say new class X. And in the constructor of it, it goes off and starts constructing other classes. And those classes in their constructors go off and construct other classes. And so on and on and on and on. So we have the same problem as we had with procedural programming, as you pointed out at the beginning. If it's a leaf class, yeah, it's a piece of cake to test. Nobody really has to explain to me how exactly I test array.sort. Yeah, piece of cake. It's a leaf. But how do I test, I don't know, the login page? Totally different end of the things. So in order to test this thing, really need something we call the seam. We basically need to be able to take a knife and then kind of cut all the dependencies. And the seam is important because it allows us to divert the execution of the code. This is why procedural programming is problematic, or rather static methods are problematic, right? Because if you call another static method, there's nothing I can do in a test to prevent that call from happening. Now, I'm sure you can come up with a simple case like, but I'm just calling math at absolute value, therefore it's OK. But usually when you have some static utility method, people keep adding stuff to it. And so what started off as a benign method call, which was non-interceptable, ends up to be this complicated beast that all of a sudden is non-interceptable, and all of a sudden it's not so good. So I take the extreme point of view, and I simply say, in my code, I don't want to have any kind of statics whatsoever. It turns out that in most cases, when I see static calls, I usually look at them and I say, yeah, this actually belongs on this class over here. And there's something wrong about the OO decomposition of the project. For example, let's take the extreme example of math.absolute value. I firmly believe that the 5 should be able to say 5.absolute value. Why do I have to say absolute value and pass in the 5? It should be just a compiler sugar that does all the magic underneath it. And I believe in languages like Ruby, you can do that. That doesn't imply that the 5 has to be an object. It just means that the compiler knows how to convert all these things. So we need to have a seam. So great. So we have a seam. And what seam allows us to do is to replace these dependencies with friendlies. Now, when I say a friendly, I don't necessarily mean a mock. It could be the real class that I'm already tested somewhere else, and I already know that it's going to do the right thing. Therefore, I'm perfectly happy to instantiate the real thing. But I trust it. I know when the test fails, the problem isn't over there because I have other tests to prove that that stuff works. It could be the real thing. It could be a stub, such as that it does nothing. Like, for example, in a logging framework, I'll just throw in a stub so that you don't bother logging anything because it's not relevant for the purpose of the test. It could be a mock which returns some collaboration. It could be a simulator kind of a thing that kind of simulates the thing, which is kind of like a smarter mock. The point here is not what you put over there. The point here that from a testing point of view, I have a choice to place anything I want over there. And that requires a special way of writing code. If you in your code just simply call the new operator on a class, well, there's nothing I can do, right? Even if you create an interface for these things, but if you instantiate the implementation of the interface, there is nothing I can do from a testing point of view. So it is really, really important to have these seams. And how exactly we place seams inside of our code, that is something that most of us are not experts at. It's not something we have learned in school. It's not something that we have learned through hacking. It's not something you even needed because unless you were writing tests already, why would you be placing seams everywhere? So how exactly do we need the seam? So let's back up and keep the seam in the back of our mind, and let's talk about something else. In most of our classes that we have object graph construction and lookup with business logic. Business logic is the if statements and the loops and the stuff that actually does work. And the object graph construction and lookup is basically your new operators when you're constructing the object graph. And it's also your let me go and find what I need code. Usually in terms of let me go talk to the context object so that I can find my property, so that I can use the property to open a file and read the parameters that I need, which makes it impossible for me to ever give you the fake parameter in a test, or at least makes it really, really miserably hard. So that's what I mean by object construction and lookup. And then the really good stuff happens where most of our bugs are, which is in the if statements and loops and etc. In most code I have seen, those two pieces are together. And it's probably the code that you write as well. But it turns out that those two responsibilities need to be separated. You are either in the business of constructing things, building object graphs, constructing the application with all the instances of the classes, or you're in the business of being those things that got constructed and doing the actual work. If you separate these two things out, it turns out testing is trivial. Not trivial, but really, really easy. So let's look at how that works out. The little bubble on the arrow represents where the new operator is located. If that little bubble started off inside of the blue class under the test, I could have never, ever controlled the construction of that class. But because I have migrated the new operator into my test, now the test has the responsibility of constructing the object graph, and then I take those objects and I pass them through the constructor of the class under test, and then the class under test then collaborates with the things that I've passed in. Now this gives me a choice in a testing world because now I am free to instantiate a subset of the application that I want to test. I no longer have to instantiate the whole thing. I simply instantiate the stuff that I really, really care about. And I have a choice in terms of how I set things up. If I choose to instantiate the real thing, then maybe I can, configure it in the correct way. So if I'm testing a cache, I'm going to instantiate a cache that has a cache size of 1 so that I'll get misses all the time, right? Whereas in production, I know I'm going to have cache size of 10,000, but I don't want to do that in testing purposes because, gosh, it's going to take forever to cause misses to happen, right? So the point is, you want to make sure that your code is kind of devoid of the new operator, because new operator is static and it causes direct binding. And you want to basically say, I need these objects to collaborate. In your constructor, you say, hey, I need the file cache. Please provide it to me. It is not my responsibility to go and read some property file on the hard disk in order to figure out how to instantiate a file cache and then configure it in some specific way. Or it is not my responsibility to do cache.getInstance and look into a global state variable, which is the instance variable of the cache, and get a hold of the cache that way either. I simply say, I need a cache in my constructor, and one will be provided for me. In the testing world, we'll provide you with some kind of a small size cache which we can go and test. And in production, you'll be provided with the real thing. So the new operator separation is important because that allows us to do subclassing. When we can do subclassing, we can take advantage of polymorphism. And polymorphism is what the seam is. Does that make sense? Now, show of hands, how many of you guys actually do this in your code? You do this. Excellent. So you know all about dependency injection. So let me ask the question again. How do you write hard-to-test code? The real crux of the problem is, if you want to make code hard to test, you're going to mix your object creation code with business logic. The moment you do that, you mix those two pieces together, you cannot instantiate anything in isolation. And when you cannot instantiate anything in isolation, the only thing you can possibly instantiate is these humongous chunks of application which pretty much cause you to instantiate the whole thing. And now we're back to square one, which is scenario-based testing. And we kind of already decided it's not a good idea. Wow, I went through this really fast today. So the takeaways are this, that we really, really want to be able to test in the form of a unit test, not as a scenario-based test. And in order for us to be able to take unit tests, we need to separate the object instantiation responsibility from the actual responsibility of doing work. You are either a factory, which is responsible for creating some object graph, or you are the part of the objects that are doing some work. You don't want to mix the two. All right, I kind of rushed these slides. I'm not sure why. So we have covered them all in an amazing half an hour. So I'm going to turn it to you guys for questions. And if you'd be so kind and grab the microphone, that'd be awesome. And maybe even come closer so you're not so far away.
I was thinking I should mention something, which is that some of the dependency injection is whether you need it depends on what language you program in. So
okay.
If you program in Perl or Ruby, you can often find a seam through the language being dynamic.
Yes, so I'm probably referring to monkey patching, right?
Yeah.
Okay. We haven't talked about the idea of global variables. But basically, global variables make your code really, really, really hard to test because things are unpredictable. The order of the test matters, and so on and so forth. And it turns out that doing monkey patching, code is in global space, and you monkey patching the code oftentimes results in you changing global state, which means if you go and monkey patch a class, and then another class runs, and you didn't properly clean up after yourself, then the new test will fail. So even though many languages like Ruby, JavaScript, etc. allow you to do monkey patching, if you do monkey patching on a class instance, you can probably get away with it. If you do it on a class level, it usually is a bad idea, and it's no different than having global state. And there's a separate talk we do just on all the evils of global state. So even if you have that, I think dependency injection is still a good idea. And I think, Paul, Dave, you were going to say something?
Yeah, I disagree.
You disagree? You think monkey patching is a great idea? Okay, do you want to give your point of view?
Yeah, what you said is exactly right. The problem is if you don't clean up properly after yourself and the next test runs in an unknown state. Right? So if you have a good framework that will ensure that things are cleaned up, then you don't have that problem.
Okay.
And generally, it's a lot less intrusive of a framework than a DI framework.
Different opinions. Of course, Dave is the Ruby guy, who's the highly dynamic language guy. I'm the static typing guy.
Yeah, so our specs mock framework does exactly that. It cleans up after itself if you step out methods to return instances and so forth.
How does it know which things you modified?
Because you modify it through the framework.
Ah, okay.
And it keeps track of everything.
So it keeps track of it and then
restores everything when it's done.
Other questions? So in Java, you have dependency injection, and you have nice fancy tools like Juice for what we call automatic dependency injection frameworks. People oftentimes confuse and they say, oh, I'm in C++, C++ doesn't have Juice, therefore dependency injection is not for me. It turns out that dependency injection, the practice, which is asking for things in the constructor, and dependency injection, the automatic frameworks, such as Juice, are two independent things. And so you can have one without the other. And you can perfectly well use dependency injection in C++ with manual, where you have to write the factories yourself. Great. Well, thanks you guys for coming. See you next week.